So, I am Jens Kristensen from the University of Edinburgh, where I'm a PhD student supervised by Grunde Jomas. As you just saw, Farah Fauci was one of my students. She worked on the project. I only have one at a time because I cannot really handle more. A girl like Farah is really, as you maybe noticed, is a so there's a lot of discussion back and forth, and that's really inspiring to have such great students to supervise. I'm, as I said, University of Edinburgh. The official, I think, title was Solar Panels and Fire Safety. I was like, that's a very wide subject, so I decided to say, okay, what is it actually I'm working with, because I cannot cover all of it. I'm working with the fire-related risk of photovoltaic installations on flat roof constructions. So what is photovoltaic installations? That is just a type of solar panels that produces electric energy. So, and the flat roof constructions, that is related to protection of property, and in most cases, large commercial installations installed on buildings such as warehouses or production facilities. In this case, my building in my head all the time is an IKEA store, because IKEA is one of my sponsors. So I'm just thinking IKEA store, that's what we have to in some way protect. Then it could also be a Target store, or it could be any other kind of store or warehouse where you can have these commercial installations. First of all, I'll give you an overview of the presentation. As you can see, I didn't get the format right, so it's not that wide, but the content is still the same. I'll give you an introduction, which of course will consist of an introduction to the topic, but also an introduction to the photovoltaic installations. What is it actually? Then it's hard to talk about photovoltaic installations on flat roof constructions and the fire safety related to that if we do not understand the fire safety related to a flat roof construction without the photovoltaic installation. So I'll also give you an introduction to that, and then we'll make the combination and say, okay, we have a solar panel and we have the PV installation. PV is the acronym, short version of photovoltaic. I'm going to say that a lot. And if you combine that with a flat roof, what's the problem? And that way we can identify the problem, whereupon I'll tell you about the research I've done. First of all, the whole project started with like a master thesis. No, before a master thesis. Ended up with a master thesis, and then it became a PhD project at some point. And we just decided to continue. Then you'll have the objective, the influence of the photovoltaic module, large-scale experiments, medium-scale experiments, and then back to the fundamental equation of fire spread, which is what the stuff that Farah did, and I'm continuing with. And then hopefully, maybe we'll have a discussion and some questions. So, first of all, introduction. The amount of photovoltaic installations have increased rapidly over the last decade due to reduction in price, but also due to the fact that people are getting more and more aware of global warming and so on. So there is an economic benefit of taking your roof construction when it looks like this and actually changing it into something like this, where you actually suddenly install a lot of photovoltaic panels on top of your roof construction. There is an economic benefit, and there's also, let's say, publicity benefit in having these panels. I think Elon Musk, the founder of Tesla, who also owns Solar City, said it's like having a money printer on your roof. Then I'm not sure if he regretted it after. Now there's a case where Walmart have decided to sue Tesla. Tesla owns Solar City and have installed solar panels on 247 buildings, and they want to take them off now. They want them off the roof because they've had 7 fires in 7 years. So that's, of course, some legal stuff I really don't understand, but I think most of you know that there is an issue with photovoltaic installations and fire. We're seeing more and more of them. But as you can also see from this data, for example, it goes to 2015. It's data from Italy, which is saying fires involving PV installations in Italy. That's the only data I have that's saying anything about fires related to photovoltaic installations. I asked the guys in Great Britain, where I'm a PhD student. I'm myself from Denmark. I've asked for data there. There is not much data So it's hard for me, actually, sometimes to justify the research I'm doing. The only thing I can say is they're happening. Please consult the news. But when the fires are happening, there's a really big German study written by Stepansky et al. It was written in German, so I had to read German. Then it was translated this year to English, so it's actually possible for most people to understand, which is saying, highlighting the consequences in case of a fire caused by the photovoltaic system. So we have an issue, and when we realize we have an issue with fires and photovoltaic installations, we have to look at it and try to understand it. And the first place to start is trying to understand what is the photovoltaic installation. It is a photovoltaic cell. It's the blue squares that you see when you see these panels. You put them in series and parallel connection. Then you have a PV module. You put them in series. You have a PV string, and then you put them in interstring connections, and then you have a PV array. That's more or less the schematic of what a photovoltaic system is. The problem is that there is a lot of probabilities of electrical faults. That means malfunctions due to the way that it's assembled, due to the way that it's produced, due to the fact that what we're doing is actually installing a large direct current system on top of your roof construction, which is not designed to install such an installation. And I'm not an expert in direct current, and I'm not an expert in arcing. All I can see at the moment is we have ignition and we have fires. So please don't ask me about, let's say, the whole electrical system. What I'm here to talk about is when we have the fire, what is happening. So that's why we're going to talk about the roof construction when we make the change here from, okay. So what is happening? Sorry, I couldn't remember my slides. So we have the photovoltaic installation, the photovoltaic cells, which is a source of ignition. But it's not necessarily the only source of ignition. And it might also be that the photovoltaic panels itself is actually causing the spread of fire. Because what we saw here, which is a big cooling storage area in Norway, they installed photovoltaic installations on the whole roof construction. The person who is aware noticed that when you go from here to here, that corner down there, the whole roof construction actually changed that area. That's because inside there was a truck or a forklift, and that forklift caught fire. The fire propagated through the roof construction, and then underneath the photovoltaic installations, and along the roof construction, and along the facade. So that means it's not only because of the fact that you actually have the ignition from the panels, but they do also facilitate the spread of fire, which our roof construction is not normally doing. So then we can ask, okay, what is a photovoltaic panel? When we look at the panel itself, what does it consist of? Is it an additional fuel load? Is that the reason the fire is propagating? The panel consists of a frame, which is aluminium, consists of glass, the front panel, consists of the solar cells or the photovoltaic cells. Then you have some encapsulate and a backsheet and a junction box. The only part which is actually combustible of these parts is the encapsulate, the backsheet, and the junction box. You know, the aluminium can burn, but then I think we agree that we have another problem. That's a really, really big fire. The encapsulate, it's a plastic. The backsheet is often plastic. And then you have the junction box, which is plastic. Then we have the cables on the roof construction, and we have the mounting system. But overall, the PV module itself, it's less than 10% of the mass that's actually combustible. So is it an additional fuel load? Probably not really. But we were looking at that. Then we have to talk about the fire safety on the flat roof construction, because we need to understand what is it actually that's happening. So if we take the probability of ignition on a flat roof construction, we do have the probability of self-sustained ignition, and we have the proportions to prevent ignition. So the more precautions we take, the smaller the probability of ignition is. If we introduce some kind of precautions, such as the obvious one, do not start a bonfire on the roof construction, then the probability of a self-sustained fire is actually smaller. We decrease it. And we can take more precautions. We can take the prescribed one. We have to ensure the safety distance to our neighbors. Then we do not have spread from one building to another. then once again we decrease the probability. And we can have other means, say, let's restrict the access to the roof constructions because human beings and teenagers having fun and not really that nice to handle your roof construction, and it also increases the probability of ignition. So you try to avoid them and say, don't go on a roof. So that's ways where you can prevent a self-sustained ignition event. At the same time, if we then go to the consequences of the ignition on a flat roof construction, the consequences are also decreased with a reduction, with the introduction of mitigation solutions. So, if we do something obvious, choose the accurate materials. Do not use combustible roof materials. If we do not use combustible roof materials, then we decrease the consequences. If we prescribe one, design the roof constructions in the right way. So ensure that in case we have a fire on the roof construction, in case it's actually happening, the fire is not spreading inside the building. That's also a way to limit the consequences. Another move, remove all the combustible stuff from your roof construction so there's no extra fuel load. Then once again, you decrease the consequence of the ignition. Then when you combine those two, you have what's called the bow tie model, where you have the probability of the self-sustained ignition event, which is completely, in total giving the probability of the initial event. And then when you're multiplying those two, the probability and the consequence, you have the risk of the roof construction. Where if you decrease the probability, you decrease the probability of the initial event, and thereby you decrease the consequence in case of ignition. Okay, so what does that mean? It means that if we have a roof construction, which I've sketched here, and a guy like me who's doing experimental fire safety, I kind of like to put fire to that kind of stuff. So we place a wood crib, and we ignite it. Then what's happening on a flat roof construction is when you have ignition, and it's actually burning, you have some kind of heating, radiation. In this case, it could also be convection or conduction. That is heating up the materials, and these materials are releasing combustible gases. It's a pyrolysis process. If the concentration of the combustible gases is high enough, then we have ignition of the material. But what is happening on a roof construction without photovoltaic panels is that because we have designed the roof as we have designed it, we can have heating of materials, but this amount of heating is not high enough to heat the nearby material, or at least release a high enough concentration of combustible gases. That's why we do not have the propagation of the fire on a normal roof construction, because it's classified according to some standards. That's how we designed our roof construction. All right, so let's see, yeah. So that means in the way that we're designing a roof construction today, we can actually increase the probability of self-sustained ignition to infinity, more or less. Because what we have done is that we have decreased the consequences because we have designed our roof construction in the way we have designed it. And that means a roof construction should not be designed for if a fire occurs. It should be designed for when the fire occurs. That means we're working with a probability of ignition that's 1, more or less. All right, so then we have the PV-related fires, the combination of the photovoltaic panel and the flat roof construction. So what we're doing is we are adding an additional source of ignition related to the PV system. But what we're also noticing is we're observing an increased number of PV-related fires. So the question is, did we not construct a roof construction for a probability of 1? Wasn't that what I just said? Do you agree? Huh? Anyone disagrees? No? Did we not design the roof to prevent the spread of fire? Yeah, we did, right? So maybe it's actually not this that's the problem. Maybe it's actually that area over there. So the question is, the obvious question, did we choose the right materials? Did we design the roof construction in the right way? Okay. What have we done? We took a roof construction which looked like this, with a roof construction and a fire in the open air, and then suddenly we placed something on top of the fire, right? So we've changed the design significantly, right? at least from what we have done for a long time. And that means that we have the radiation of the heat back towards the roof construction. All right, so the big question is what should we do? And one thing to do, trying to keep our buildings safe, is trying to look at the insurance companies and have a chat with them, or at least look at their guidelines. So I looked at their guidelines, like a large insurance company, let's say one of the biggest in the world. They have a nice guideline for photovoltaic installations on commercial roof constructions. There is 28 recommendations. 20 of them is related to the photovoltaic system itself. How to design it, how to connect everything, which panels to use almost, like what kind of mounting system. Everything is related to the photovoltaic system itself. 3 of them is related to the building that's actually hosting the photovoltaic installations. The first one is more or less strongly discourage combustible roofs. Is that any different from what we're doing before? Not really. The next one is saying limitation of array size of 2,000 square meters in total. That's a freaking large array. And then there should be a gap distance of 1.2 meters in between the array. So just telling something about how large should the array be, and that's limited to the equipment of the firefighters, if they should be able to reach it. What they should do, no one really knows, but someone came up with some numbers. And then routing of cables should not compromise fire compartments. That also seems kind of logical. But the only thing which is actually related to the spread of fire is the one that says we strongly discourage combustible roofs. That's all I could find. But in my head, the focus on the potential ignition source is a quick fix, because it's the best solution when you do not know how to mitigate the consequences. Of course it works to focus on the ignition source, the photovoltaic system. But that's because we do not know anything about that roof construction. We do not know how we actually changed the fire dynamics. So that's what we decided to focus on, try to understand. And that's where we try to do something called research. We put things on fire and try to understand what's going on, and try to explain it in a scientific way, or at least trying to get more understanding so we can have, what should we say, recommendations for companies and people who want to install photovoltaic installations. So, as I said, I started this project before I wrote my master thesis. Then I wrote a master thesis, then we continued. More companies want to join. I'm sponsored by 3 companies. IKEA Services, who is owning all the property. I guess they're called Inca now. Then Kingspan, installation company, and Rockwell, who is also an installation company. So it's 3 multinational companies who are interested in the topic, and that's really great because it actually makes it possible for me to do the research that I want to without thinking too much about economy. Thank you. So, first of all, the objective. Before we talk about the objective, we should put some kind of boundaries on and say, okay, ignition will happen, either due to the photovoltaic installation, but even if we decrease the probability to 0, we'll still have the standard probability of ignition on the roof construction. So we say ignition will happen due to the PV installation or due to other ignition sources. The cause of the ignition is not the main focus. What's interesting is what is the fire dynamic behavior of the system, where the system consists of the roof construction itself, the photovoltaic panel, and the fire. And then when we have that understanding, the question is, how do we mitigate the consequences? But it's pretty hard to mitigate the consequences if we do not know what's actually going on. So what did we start with, or what did I start with a long time ago now? We started with a setup, with a gas burner, with some heat flux gauges that we could move horizontally. Then we could reduce the heat release rate from the gas burner, and we could measure the heat flux as a function of distance to the gas burner. Not really rocket science, but we tried to understand the influence of the PV module itself. It looks like this. Not rocket science either. You have the distance from the heat source down here. You have the heat flux up here, and you have the heat release here. As you can see, it's symmetrical, and it's decreasing as a function of distance, meaning if I'm standing here, it's really, really warm. If I'm going out here, the heat flux is quite low. The interesting thing is actually what's happening if we install the photovoltaic panel on top. In the real world, it looks something like this, where you have the gas burner, obviously, the heat flux gauges inside two pieces of insulation, which could be moved horizontally, and the photovoltaic panel. It looks something like this, where you can see that you had significantly higher heat flux. Where do we go? Here? Underneath the most elevated part of the panel, whereas below the less elevated part of the panel, we have a lower heat flux. Also, the heat flux is exceeding the 6 kilowatts per square meter, which is a critical heat flux for the roofing membrane. That's something we tested in the cone calorimeter, if any of you know that one. It's a piece of equipment designed by Bobrowskas, but where you can figure out how much heat should we actually apply to a material before it releases a high enough concentration of combustible gases to have sustained burning. So why did we have the highest heat flux underneath the most elevated part of the panel? Because in my head, if we just heated up the panel and the panel was just a warm surface, due to the view factor and due to the fact that the least elevated part of the panel is closer to the heat flux gauge here than this part of the panel, this one should actually be higher. But what's happening is that you have the deflection of the flame, and thereby you have an increased amount of radiation towards the heat flux gauge. So what did we conclude? Or what does that mean when we look at our roof construction again with our small nice wood crib? And we decide to put up our photovoltaic installation. That means that when we ignite it, we have the ignition, we have the heating of materials again, but due to the fact that we're actually deflecting the flame, the heat here is higher towards the roof surface than before. That means we'll have a larger area which is affected, a larger area which is heated, which will release a higher concentration or a higher amount of combustible pyrolysis gases. And that means if the concentration is higher and not too high, that's important as well, then you'll have a larger fire. And instead of the design of the roof construction stopping the propagation of the fire, you'll have a self-sustained flame spread. Because now you'll have an increased amount of heat, pyrolysis gases which are released. That means you'll have a larger fire, and thereby we have an even higher amount of heat which is released, and then the fire just continues to grow. So, the PV installations can stimulate the spread of the fire. The probability of ignition and increased fire load is not the only risk. And then the results of these experiments showed that it's definitely the base of discussion of which materials are we actually using on the roof construction. Is it the right materials when we have this design? Then, of course, there were some limitations. It was an optimized scenario, 1 parameter bench scale. We didn't have any wind. We didn't have any cables. We didn't have the junction box. We had to do something else. And what do you do when everything is more or less possible for you doing your master thesis? You say, we verify it on full scale. Why? Because then we had a realistic roof construction. We had multiple PV panels. Instead of just one panel, we would have multiple panels, and then we could say, okay, we can test different mitigation solutions. So we could take a worst case scenario, which in our head is an expanded polystyrene roof construction, like insulated with that sounds like something that's burning. We tested that earlier with the insurance company, so we realized just having the EPS expanded polystyrene and then building something on top of that was probably really a waste of time. But the insurance company did it, and we looked at it, and we saw a bonfire, a fire. So we skipped the part that was just the EPS insulated roof construction because we realized it burns, and it has nothing to do with the PV panel. It just burns. So what did we do? We I designed a setup where we had east-west orientated array. That means we have it as a tent, as you can see. Then we had EPS. I'll go to next. Yeah, we had some dimensions, not really important. We had a commercial mounting system. We had PV panels. We had a roof construction. We had two different widths. We had one that was 1.4 meters, and we realized that was not really too good because we had some edge effects here, and we actually couldn't see what was happening out here on the roof construction, so that wasn't the best design. And we made another one that was 4.8 meters instead. Then if we focus on how we actually constructed the roof, we had the existing roof construction, which is what we called it, which was a light roof construction, self-supporting metal sheeting. We had some EPS insulation, and then we had a roofing membrane, PVC-based, I think. On top of that, we had the mitigation layer, which was either 40 millimeters of PRR insulation with the roofing membrane on top, or it was 30 millimeters of mineral wool. And those two products was what was available to us at the time where we wanted to do the experiments. And that's, of course, also an important part. We cannot just design our products as we want them. We try to use what's actually available. Then on the side here, we had some vertical protection because in those experiments designed by the insurance company, there was no vertical protection. And when you have a fire up here and you have something which is highly combustible here, which is releasing gases, then suddenly you have ignition from the side. So we had to protect the setup from the side so we didn't get ignition that way. In between here, between the mitigation layer and existing roof construction, we had a bunch of thermocouples. I'll show you how. This is the top view of the setup with a total of 6 panels. We ignited again with a wood quip of approximately 14 kilowatts, as far as I remember. I can't remember it exactly right now. It's somewhere in the paper. But if we have a more simple overview, made in MATLAB. The setup looked like that. We had the point of ignition, and we had, as I said, a bunch of thermocouples installed. When we installed them in this way, I learned that from this first series of experiments. If you just install them in lines, you cannot do anything cool graphically. If you install them like that, you can do something like this, and then you can see the development of temperature below the mitigation layer as a function of time. And you can do some beautiful simulations. So we had a total of 4 experiments. 2 of them were the small ones that were 6 meters times 2.4, and 2 of them were the large ones, which were 6 meters times almost 5 meters. The main focus of the presentation now will be on these, or on the next part of the presentation. It's still just a small part all in all. In the real world, they look something like this. This is one of the small ones. You had the ignition at the point D, and then we had a lot of equipment and some thermocouples, and that's it. We could definitely instrument it heavier, but my experience were not that high at the point. From the top, the large ones look like that. All right, so the next question is extent of fire spread. So did it burn? Yes, it burned. What is interesting is you had these plumes of smoke, and as you can see, you also had a pretty high heat release rate. This is mainly the roofing membrane which is burning, because that's more or less the only combustible on the roof construction. But the interesting thing with this setup that we tested was that these plastic foots of the support system, even after the fire was completely gone, they just continue burning and continue burning and continue burning. We extinguished them at some point, but they were definitely not flame retarded in any interesting way. They were probably flame retardant and probably standardized according to some standard, but in the real world they performed differently. So extent of fire spread, if we look at the 2 large experiments, and that's in my head what's interesting, is if you look at wind direction in general, the fire did not propagate outside the array. You only had that area down here, and the propagation of the fire, or the ignition of the roofing membrane, the other one looked like this, happened due to deflection of the flames from the main fire, so the large fire that we had when we had ignition underneath the roof. As soon as you didn't have the deflection of the flames due to a lack of wind load, then it extinguished. So we didn't have any self-sustained spread of fire outside the array. Sorry. Underneath, that's really interesting, what happened with those thermocouples. In the test with the 30 millimeter pier, you see it turns from blue to bit lighter blue, so it reaches something about here, 200 degrees. What's interesting is what happened underneath the pier insulation, because after 1 hour and 2 minutes, you had suddenly a big increase in the temperature underneath the wood grip. And then with time you saw, whoops, the temperature is increasing again here. And it continued over here as well. So we had a solid amount of smoke, and we had to ask the firefighters to extinguish, just so we had something to look at afterwards. And what happened in the test with the mitigation layer of the pier, after 1 hour, the insulation was, what should we call it, thermally degraded, so the mechanical strength was really not there anymore. And that meant when we removed the mitigation material, the insulation, we looked at something that looked like this. It was a very, very warm day, so we had a lot of cola, and we were a bit too lazy, simply because we were exhausted. Danes are not used to temperatures of higher than 20 degrees, more or less, and it was very warm. Anyway, what we noticed was this large area in the EPS installation, where you can see these black spots. We noticed some charring. We definitely had all the signs of ignition. When we then compared that to the test with the mitigation layer of mineral wool, we at least did not have any penetration in the mineral wool. But when we removed the mineral wool, we had also a very large area which were affected. This area is actually significantly larger than the area with the pier insulation, but there's no signs of combustion. It's all melted EPS. So it's vaporized is the right word. Due to the increased heat, so we had temperatures of, let's say, 100, 150, I can't remember the exact numbers, but that means that DPS insulation is actually vaporizing. But we did not have any ignition source, and thereby we did not have any ignition. Why did that happen? Maybe because of the thickness of the materials. One of them were 40 millimeters, one of them were 30 millimeters. So it's two different thicknesses, and thereby the heat is transported easily through. So what did we learn? The photovoltaic array, again, facilitates the spread of fire. Yes, bingo, that's the same. The fire propagate outside the domain of the wood grip? Yes. What does that mean? It just means when we have the initial ignition, no matter what it is, because there's a lot of people who complain about me using a wood grip, but is it interesting if the wood grip is here and the fire is already here? You know, when it's fire propagated to here, it doesn't really matter what ignited. What matters is the fact that the roofing membrane is continuing burning, right? So that's an interesting thing. So when it propagates outside the domain of the ignition source, it doesn't matter what ignited. What matters is the fact that certainly what is normally not facilitating spread of fire or not burning is burning. So that was what was interesting in this case. And then the fact that the fire does almost not spread outside the array, because when you're outside the photovoltaic array, you do not have the re-radiation, and thereby the total amount of heat towards the roof construction is limited, and the designed roofing membrane is therefore ensuring that the fire is not propagating. All right. Of course, there was also some limitations of this. It was an outdoor experiment, limited control of the environment. We had limited instrumentation, limited number of experiments, because these experiments are kind of expensive, and also because, for example, the PV panels, there's not really many people from the PV industry who wants to talk with me. And I do find that very, very interesting, because if you're looking at what I'm doing, I'm actually working in the interest of the industry, right? Because the alternative is just say, let's ban it. But I'm actually trying to ensure that we can continue installing photovoltaic installations, because it is the future, and we just need to understand it. And when we have the understanding, then probably no problem. All right, so what do? Medium-scale experiments. So we go somewhere in between. Realistic fire load, controlled environment, flexible instrumentation. Whoops, that was really good. So then, it's a part of my PhD, certainly. And I had a student, and I asked him to do some designs, and I learned a lot of stuff having the first student. So we made a design. And that consisted of a PV panel, again, this aluminum profile setup. Again, we ignited with a wood grip because it was reproducible source of ignition. The arcing, DC arcing, is kind of hard to make it work really properly. We just figured that out. We had the roofing membrane. We had some heat flux gauges outside the panel. We also had some heat flux gauges inside the panel. Then we had an induced flow, or that was our plan at least, and we had an extraction head. So we could do all of it inside. Perfect. All right, so we realized that the roofing membrane, there was a bit too much. You saw how much smoke that we had in the previous images, and the lab manager in Edinburgh wasn't too happy with that. Then we had the induced flow, which if you have an extraction hood which is this big and you have an induced flow, then suddenly you have your smoke outside the hood. He wasn't too happy with that either, so we removed that, and we had this experiment. From the top it looked like this, with the photovoltaic panel, with the heat flux gauges, and with half a square meter of roofing membrane. You'll see that's plenty. And the wood grip, and some different instrumentation. We did a series of experiments, one with no panel. The one with no panel, we didn't have any spread. 5 centimeters maximum away from the wood grip, that's it. Use PV panel, new PV panel to see the difference, and then a new PV panel and the wood grip removed. So, medium scale experiments results, to be honest, limited scientific value, but really great visual understanding. So the results that we got was really limited. I couldn't really use them for much. But this video is awesome, in my point of view. So we have the wood grip there. We have the roofing membrane. You can see it here, and then along this red line. And then down here we have the heat fluxes measured. We had the extraction flow rates. And then we'll just see what happens with time. So we increase the speed a bit. We'll see, okay, now the roofing membrane is slowly heated. We have ignition of the roofing membrane a bit. We have some dripping from the panel, very limited. But the fire is propagating, a bit outside the wood grip itself. It starts igniting the roofing membrane. And there we go. So suddenly now we have the roofing membrane ignited, which is producing a solid amount of heat. And now it's not about the wood grip anymore. It's about the fact that we have a pretty big fire below our roofing membrane, and the flames here are deflecting, feeding heat back towards the surface of the roof construction, and thereby we have the propagation of the fire, and the fire is just spreading underneath the panel. Nothing spread really outside the panel again. That almost costed a camera. But I think it was worth it. Also because you can see here that you see some very high heat fluxes suddenly. And once again, these heat fluxes are above the critical heat flux of the roofing membrane. So this is what's happening underneath a PV panel, in case you have ignition and in case you actually manage to have the initial self-sustained fire, no matter the reason. So that's why I like the video, although the scientific result was limited. So what do you do? What's the status after the medium scale experiments? Well, we understood why the fire propagated. That was, as you've just seen, I've tried to explain it. I think most people understand. It's an increased amount of heat towards the roof construction. But we really didn't have any understanding of the influence of the materials, influence of the roofing membrane, influence of the PV module backsheet. Is it actually impossible? Is it important? Is it combustible? Is it non-combustible? Is it actually supplying an extra heat load towards the fire? Didn't really know. Geometry? Didn't really have any understanding of the elevation of the panel. We didn't really have any understanding of the inclination of the panel. All in all, it was a series of pass-fail tests without any scientific value. In another presentation, I called it the Great Depression or something like that. So, in general, there was way too many unknowns, way too many parameters that I didn't understand in any damn way. So that was kind of hard to realize. So what do you do when you don't really understand what's going on? You go back to your literature, You go back to your books, you go back to your papers, and what you'll often do if you go far enough back, and what will happen if you go far enough back, is you'll end up with this guy, Foreman A. Williams. He used to be a professor, maybe still is, at Howard. He's not that young and handsome anymore. He's a very old man, I think. But what he did is he introduced the fundamental equation of fire spread, where you can see that the heat flux, or heat, is proportional to the velocity of the flame, the speed the flame is propagating. And then you have some constants, density of the material, and inertial difference of the material. But that's constants related to the material that we're using. Quinteri, who's another of the big guys in fire safety engineering, continued with that, or let's say expanded it, where certainly you can see if you have a fire that's propagating, then you have the release of some mass, and you have the overall heat flux produced by the flame towards the preheating zone. So the more heat I'm adding to the preheating zone, the faster I'm heating it up, the more combustible gases is released, and thereby the faster the flame is actually spreading or propagating. That also means that if this value is high, certainly this area will be larger because you have a faster heating of the material, so your pyrolysis zone will be wider. That means you'll have a higher release of combustible materials and combustible gases. That again means your fire will grow. Your preheating zone will be longer, it will go faster. So then the other problem, the materials, as I said. We had the roofing membrane and we had the PV module. That's the two main materials. The roofing membrane is one membrane. It's not representative of all membranes. A bitumen membrane is not similar to a PVC membrane. And a PVC membrane is probably not similar to a PVC membrane from another company. So we have a lot of unknown properties we really don't know anything about. Unknown parameters. And then they're flame retarded, so that's also kind of a problem, at least if you want to have the initial ignition of the fire. So what did we do? As Farah said earlier, we used black PMMA. PMMA is acrylic plast. It's studied a lot by the guys in America, mainly a man named Fernandez Pello, who is a professor at Berkeley, and his students. They're doing, let's call it basic understanding, fundamental, I guess is a better word, understanding of simply propagation of fire. They studied a lot. It's well-known properties, and then because it's black, we assume that the absorbance is 1. That means that we assume that all heat, radiative heat towards the surface is absorbed. Then the PV module, again, one module is not representative for all modules. Is it combustible? Maybe. We really don't know. So we replaced that with something we actually knew what was, black body surface. That was basically, it's non-combustible and it's reusable. Because of what I told you earlier with the PV panels, we're not going to use too many of them so far at this stage. Basically, it was just a stainless steel plate, 3 millimeters thick, painted black with some really expensive paint shipped from America, which burned off in the first experiment. So then the panel was suited instead. So still black, and still completely black, and thereby still a black body surface. Well-known properties, not used yet. So some of the stuff I'm talking about here, about the assumed absorbance of 1, the well-known properties, it's stuff that I've been thinking about. It's stuff that are introduced in some analysis I've done, but it's not stuff I'll introduce to you because I've submitted it for this big fancy fire safety engineering conference, and thereby I cannot present all of it. But I'll present what's interesting from a fire safety point of view, also because I'm still sure I could do a better analysis on the results I got. So what did we do? As far as showed, we had this PMMA sheet, 2 millimeters thick, with some thermocouples inside. We had a camera, and We had a strip of ceramic paper that we wetted with methanol, so we had an initial fire. And then the fire could propagate as a function of time, and we could record that, and we could analyze that. Bingo. Then, in some experiments, we'll put a panel on top and see the difference. From the side, it looked like that. My favorite part is the laboratory jack, because that made it possible for us to change the distance between the fuel and the non-combustible surface, and thereby we could change the gap distance. So far, we have not changed the inclination. That's, I guess, the next step. But at the moment, this board is 40 kilograms, so it's not a one-man job. It's going to be, I have to think about to make a good solution. All right, then we go back to the formula. I won't use too much time on that. We have some constants, or assumed to be constant, and then we have some values, which we can determine in our experiment. That means certainly we can calculate the amount of heat that's actually going towards the fuel in the preheating zone, and that's ideal. Then we have the combined heat flux towards the heat flux gates, and what is that? It's just a combined heat flux. So in the experiments, it's this. That means it is the combined heat flux is equal to the heat flux from the flame, the heat flux from the deflected flame, certainly, the heat flux from the heated panel, because certainly our panel is not 20 degrees warm anymore, and when it reaches a higher temperature, suddenly you'll have actually a significant amount of radiation from the panel, and that's just all of that going towards our heat flux gauge there, measuring the heat flux towards that point. All right, so what's different than the experiments? You saw these pictures before. I'll just show you more or less the same. And you'll see that there is the difference, that you have to experiment with no panel. As Farah showed you, you have to experiment with a 15 centimeter gap distance. And the difference is that here you do not have any significant change. The amount of heat going from here towards the preheating zone is constant. The width of the pyrolysis zone is constant, and thereby the whole spread of fire and the velocity is constant. Whereas here, you're just slowly increasing the amount to the preheating zone. Thereby, your pyrolysis zone gets wider. You have a larger area which is burning, the pool fires. The wider your pool is, the higher is the release of combustible gases, and thereby the higher your flames. So that's why the flames are slowly increasing in height. And when it reaches the panel, you have the deflection of the flame. Then suddenly you not only have heat from the flame, which is vertical, but you also have heat from the horizontal flame. So that means the amount of heat towards the preheating zone is increasing even further, and that means it goes significantly faster, and your fire is actually, let's say, accelerating rather than being constant. Also, what's interesting here is the length is the same. Let's say the time is significantly different. Here it took 19 minutes to reach from one end to the other, and the other took 110 minutes. I guess that's even one of the faster experiments. Is there any questions? Because it's going quite fast for me. It's the first time I'm done, such a presentation. Yeah? Everything seems clear? I'll just take some water. So, I had a problem because when Farah was done, I just continued to experiment, and that's a lot of experiments, that's a lot of videos, and that's a lot of data for my small MacBook, at least to cross that. So I need to figure out a smart way where I could not just, try to do everything at once and have like the full size of videos and just analyze that. So what I came up with instead was, what about if we just follow the green line there, one line of pixels, and saying where is the flame front at this point of the time. So if we follow that line of pixels and doing something like that, boom, then you can see if we increase that one line of pixels here, you'll have 1 pixel from half to 1.5. I don't know why it's that, but in total it's 1. And then you'll have the distance in pixels. People who know something about video recording will say 1280. That's the width of a standard image on a video, or some videos at least. And then we can see as the fire propagates, We have a line here, and initially it's just blue. That's the initial flame. And then it's propagating as one line along the pixels. What we can do with these few pictures is we can stack them. So then we have 1, 2, 3, 4, 5 different points in time. And we have the distance in pixels. We can refine that. Then instead we're just doing it for every 5 minutes. Put them on top of each other, then we can see suddenly we're going from one end of the experiment to the other end of the sample. And we can do it for every second. Then it looks like that. All right, so why is the fire starts here and here? That's because that's where the sample actually started. All of this is just like, isn't really important. So we have to identify the irrelevant data. And left of the experiment setup, and we have a reflection, so it doesn't really matter. We have the right side, doesn't really matter. Then we have the top, that's the start of the experiment. We have the bottom, that's the end of the experiment, because the flame front reached the end of the PMMA. That means all the stuff down here, it's just the fire getting smaller and smaller and smaller as the fuel is combusted. But it doesn't really matter in my head, because what we're interested in is when the fire is going from here to here. In this, at the moment, I'm not really interested in what's happening in the back. Any questions to this? Because this is a plot which is making people a bit confused. No? Great. All right, so the distance in pixels. That's a funny distance. So we have to change it to millimeters. We can do that by a big chessboard. In this case, I also realized that X amount of pixels is equal to X amount of millimeters because I knew the length of the sample. But I also had this chessboard, which is just checks of 1 centimeter times 1 centimeter. Then you put it in front of the camera initially, and you know at least that that is 1 centimeter times 1 centimeter, and you can go into a MATLAB program, and you can tell it, boom, 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 that's 1 centimeter. So it can calculate, okay, this amount of pixels is 1 centimeter when it's in the center, but when it's out here, it's only equal to 9 millimeters, or something like that. Or 1 centimeter is equal to another number of pixels. So what could we do? Now we go back to the same experiments, and say this is the one with no panel, this is the one with the 15 centimeter gap. You can see here that the time from ignition is significantly larger. Here we are 7,000 seconds approximately, here we are 900 seconds. You can see there's a very big difference. There's also a very big difference is how it's actually behaving, but we'll talk about that later. What we could do then with these pictures is we could ask the computer, MATLAB, to translate it or transform it into a binary image. So that's just a lot of ones and zeros, where the whites are ones and the blacks are zeros, or the other way around. And this is certainly a matrix, and we can just say what is the location of the last one or the last zero. And we could identify that as yellow dots, and then when we have all the yellow dots, we can say, okay, make a nice plot or make a nice fit. And then we can go from here to here and say, that's the flame front. That's the front of our flame as a function of time. Then when we take this picture and just turn it around, we have time and we have the distance. And we have the distance as a function of time. And we can do way too many of these experiments. I've done that. And you'll end up with a plot that looks something like this. That's from the stuff that we have submitted. Hopefully it's accepted. But where we have a nice plot where you can see the location of the flame front. So this is where we ignite it. Then we have 10 centimeters, 20 centimeters, 30, 40, 50. Then we have the gap height as 22, 20, 17, 15, 12. And you're thinking, where's the experiment where we do not have a panel? Well, it's because it's the relative flame spread rate. So it's the flame spread rate compared to the experiment where we do not have a panel. That means when we have a gap height, as Farah showed in her experiments, a gap height of 22 centimeters or 20 centimeters, the relative flame spread height, flame spread rate, the flame spread rate compared to for a gap of 22 centimeters is only significantly faster. If we see here, that's 2. So it's only twice as fast as without the panel. Then when we decrease or reduce the gap height to 20 centimeters, nothing really happens. You still just have a flame which is propagating twice as fast as when you do not have the panel. And we reduce it to 17 centimeters. after 15 centimeters of the sample, suddenly the flame is propagating or traveling significantly faster where we are here. So that's suddenly 17 times faster. And if we reduce the gap height even further, we can see, okay, it actually, first of all, it goes really fast before it's traveling faster and faster, but it's also ending up with a relative flame spread rate, which is almost 30 times faster on this material, due to the fact that we have introduced a panel on top of the fire and the total amount of heat towards the fuel is increased. Right, summary of current work. So we have some critical gap heights. A reduction of 3 centimeters leads to significant changes in the flame spread rate. That's what we just saw when we went from 20 centimeters to 17 centimeters. There's a big difference in how the fire is propagating. No significant changes when the PV panels are used so far with the experiments I've done. But I have 35 panels back home now, and when I'm back tomorrow, I'm going to go in the lab again, and then I'll use the 35 PV panels, and then we then have the data for experiments conducted with PV panels, and we can compare that to the experiments conducted with a non-combustible surface and say, is there any significant difference? And is the combustible backside of the panel interesting? And is a PV panel just behaving as a PV panel? Is a PV panel just a PV panel or module? Is it the same? So far I realized that some of them are dripping and burning a bit. Some of them are not really dripping. So that's the difference. The interesting part of that is then, if it's dripping, does that mean that the flame spread rate is faster? Or does it just mean that I have to protect all the equipment I have nearby way better, because that was the problem? Then also, yeah, that's actually not really interesting for the stuff I've shown you, but of course the width of the fuel I'm using is interesting. The wider it is, the more heat is transferred towards the center, and thereby the fire is actually going faster. So I have to figure out, is there if the sample is very wide, which is the case with the experiment on a roof construction, is that interesting? Because also our ignition is only once, but there's a lot of questions still. So I still have a lot of stuff to do. Also, what I've done with the new student is I'm continuing these experiments that I designed together with Farah, but we're trying to increase the complexity. So that's, let's say, influence of increased complexity. Yes, that's the future work. So now, instead of just having a PMMA slab or sheet, a lot of us will say it's not something you put on the roof. Why do you do it? It's to have the understanding, the basic fundamental understanding of what's happening. Then the interesting thing is actually, how is that related to real roof construction? So now we're starting to build small mock-up roof constructions in the lab, and we ignite them, and we see how is the fire propagating, but also how is the heat and the fire traveling horizontally. And when we have something that's close to understanding of that, then that's when we go back to do large-scale experiments. And the plan, hopefully, is to do some large-scale experiments within the next year. At BRE in London, north of London, where we can do it inside in some burn holes that can handle 6 megawatts of fire. That's not what we're going to do. It's just capable of hosting us. So that's the plan. Then, acknowledgements. Thank you to Farah, who just won the prize. That was awful. Not awful, awesome. Don't say that. And then Ming Xiang, who was the previous master thesis students. Both of them are from the International Master in Fire, Master of Science in Fire Safety Engineering, which is where they also visit Edinburgh now and then. And then, of course, thanks to my sponsors, IKEA, Kingspan, and Rockwell. Yes, that was actually it. I don't know, I probably have some extra time, so I hope some of you have some questions or some critique. Yes?
I have two questions for you.
Yeah?
One is the only reason why you are not testing wind is because the last limitation you have?
The wind?
Yeah, or you already know that it's not important.
The problem is if I also introduce wind, I'll just introduce another unknown parameter which I cannot control, or I can control it, but before introducing the wind, I'm not really smart enough at the moment to do that. So it's simply not introducing too many unknowns at the same time, because if we introduce 20 unknowns, we don't know which handle we are actually adjusting. It could just be we're adjusting a bit here, a bit here, and a bit here, and a bit here, and suddenly the experiment or the experimental, the result is completely different because we changed too much. So at the moment, no wind. With time, probably. It's probably not going to be me, but I really hope. Looks like there is some groups who are applying for funding, where Edinburgh is probably included from the European something, and that means that hopefully there will be some more research in the future. I'm really the front of the research. It's pretty nice to be that, but also means that there's a lot of unknowns, and also means that the stuff I'm doing, even my parents understand it. It's not really that complex, but it's also why it's really nice to do, because you're actually able to tell people about it and they actually understand what's going on. The other question.
The next one is, so you tested the 20 centimeters, the 22 and 17. So you know there is some consequences, and there is high propagation and all this nice. But did you reach like the minimum distance? For example, you have a cavity of 10 centimeters, so 95 millimeters something. There is no high propagation.
No, we did not do that. What we saw when we did 10 centimeters, let's say it went really fast, and I started getting worried for my equipment, to be honest. So we stopped it there. I didn't see any reason to go with experiment that took 12 minutes suddenly, or 15 minutes. I can't remember the exact number. But the trend was it went faster and faster, and just the fact that you have a gap where you have the interaction, and it actually doesn't matter if it's horizontal. Now we figured that out, and we have guys in Edinburgh, and I guess guys all over the world, who works on a vertical situation where you have an existing building and you have some cladding material and you have a gap and you have a fire which is normally propagating quite nice. So that whole idea about having cavities on the envelope of your roof is interesting. I don't think it will have. I don't know, but I don't think that it will have any. You will have a minimum gap height. I don't think so.
Got a question one, and you was from guys who make the solar panels.
Yeah.
And they say like if you have something like 10 centimeters, then you are safe. If you are 95, then you are not safe. So it was like 5 meters different. I don't know if they kind of.
I would love to see the results, and I haven't seen any results that shows that. And a really small gap that would definitely be interesting. But you also have, due to the nature of the PV panel and how it's constructed, you have a constant of 4 centimeters behind the glass because that's your frame. So that's as with a standard rigid PV module. Then what's happening if it's suddenly built into the building? Really don't know, because we're in front of this experiment or these experiments, and when we have an understanding of that, hopefully someone will look at the next step. And anyone who asks me related to doing research, unfortunately not many people, but the people who ask me, there have been some people from RISE in Norway asking, it's like, I'll help them, all I can help them, because this is just a project about ensuring that it's safe to install the photovoltaic installations, and I know I'm doing some okay research, and if I can help other people, that would be awesome, because then we can combined, hopefully, solve the problem. I do also know that there's people, NFPA in the States have designed some really nice experiments, but they need 100 panels, so they haven't started yet. They have been waiting in 3 years so far, so that's kind of an issue. The collaboration between building, fire safety industry, and the PV panel people, unfortunately. Yeah, any other questions? Did I answer your question? The answer, yeah, yeah. Yeah, and I've done that, and I'm gonna do that now when I go home. I have the 35 or something.
When you use them, there's some drive involved, and PGA spoils and stick everything together, and
Yeah,
so the back panel.
yeah. So that's the big difference, right? That you have.
Does it not like either melt or crack, so
The glass can really tolerate a high amount of heat. I realized when we did the large-scale experiments, like really a high amount of heat. It just cracks in the end and in some really big pieces. When I do these experiments, it doesn't crack. I don't have pictures of it, unfortunately, not here in the slide. But you just have an area of the combustible materials, the backside, which is often T-flat. It's some plastic, often made by DuPont, on the backside, and it burns, okay, but the thickness is so limited that it's very limited, the influence from that material. So we do not have any. Of course, we have a deflection, a very small deflection. We even have that on the stainless steel board. Yeah, all of it is deflecting a bit due to the heat, and it's really nice to see if I forget to turn off the video camera and then speed it, because then you can see that the panel is deflecting, and then when it's cooling down, it's going back up. So that's happening with all of the materials. So that also means that the panel during the experiment is actually not completely horizontal, but there's not much I can do about that, and that's also similar to the real world. So, yeah. 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 T2, I think. That was yeah. That was based on the fact that I was staying in Denmark, and I can't remember if it's T2 or T3. These two are used in Denmark and the UK, and I can't remember what belongs where. I've tested, the thing I've tested so far is the T2 and T3 classification of the roofing membranes, and when you test the critical heat flux for those two materials, it's the same. So in that case, there is no big difference. Of course, the test method the test standard method is different, but if we test it just in the cone calorimeter, the results are the same. Anyone else, please? Otherwise, you're free to go. So, and just, ask me in the break if there's anything. I don't think there is any, of course, as usual, no stupid questions. But anyway, if you just want to ask me, then do that. I'm disappearing straight after the next presentation, as we have to catch a plane. So, good. Thanks.